Hello and welcome to Lecture 15 of the Air Distribution Engineering course. Today we're going to learn about how to select a package air conditioning unit. We talked last lecture about the differences between package units and split systems, and so today we're going to focus on actually sizing and how to select, not sizing, but how to select the actual unit using manufacturer catalogs. I'm not going to go through the lecture viewing protocols or the reading schedule, so I'll leave that to you to read. Let's start with a little review. First of all, last time we understood that the refrigeration cycle 50 years ago used to have components that had to be individually engineered and then put together in a system that worked correctly because manufacturers only made the individual components. We also learned that as technology advances, I don't know if I specifically pointed this out, but let me just point it out now. As technology advances, typically equipment begins to encompass more and more components and perform more and more functionality, thereby relieving the engineer of some of the tasks. And this can be advantageous because the controls, the safety switches, the sizing, for example, of the refrigeration piping within the unit and so forth and so on, is then taken out of the engineer's hands, and the engineer can then focus on other aspects of the design, like, for example, energy savings or comfort for the occupants. The disadvantage of that, as we learned last time, is that package units are limited in scope. You have to really understand when and where they can be applied. Otherwise, you are going to potentially use a package unit for an application where it absolutely should not be used. And in this class is one of the focus of this class, you might say, is to help you understand how to apply the package unit to your specific building and your specific system. You, as an engineer, can never just decide that if you need, for example, a valve somewhere or a fan somewhere, you can't just say, oh, well, here's a fan or here's a valve, I'll just use this. You still have to engineer that valve or that fan or that package unit for the specific application. Otherwise, and I'm being facetious just to make a point, you could believe that you could go up to a large dam like the Hoover Dam in Nevada with a glass and call up to the engineering office and say, excuse me, could you please open the gate? I want to fill up my cup and have a drink of water. The valve for the dam is not capable of doing that. And as an engineer, it's very important that when you select package units, fans, valves, or whatever it is for your application, that you confirm that the piece of equipment will fit and function in your system. That's especially true with package units and equipment that has started to encompass more and more features. You have to understand what those features are. You have to understand the capability of the unit that you are selecting, and you have to understand your building well enough to make sure that they fit together. We're going to do that today. Little review again. We talked about split systems, how the refrigeration cycle can be separated with an outdoor unit and an indoor unit and joined together by some refrigeration lines. So this is a system that we're not going to really focus on today, but it is an important system in the HVAC industry. It's used quite a bit. But today we're going to talk about the package unit, specifically for your projects. And next lecture we'll talk about duct furnaces and how to select the furnace component as well as the fan component for the projects. I have a note down here. Today we will learn how to size both. That's not true. The next lecture will again talk about duct furnaces and fans. Okay, so before you select a package unit, there's a certain amount of information that you need to get together. First of all, and I'm going to assume that this is already done for your project, you have to perform a cooling load calculation using a load calculation program. You have to separate the space sensible loads from the unit loads in your calculation. And in your projects, you should have already done this through the macro. Again, the system's checksums report is where to find the space loads during the block peak of the building, and it is not equal to the sum of the peak space loads almost all the time. Now, we've already learned about that. You could go back to the load calculation lecture if you don't quite follow what I'm saying. You need to calculate the outdoor air sensible load. Now, I haven't shown you how to do that yet, but that needs to be done before you jump into selecting a package unit. So we're going to go over that. And you also need to calculate the fan heat. Excuse me. Again, that's not something that you've done yet, and we're going to review how to do that, but it has to be done before you, again, select a package unit. This slide is a little bit harder to read just off the presentation, so you may want to take the PDF and zoom in, or pause the slide and zoom in. What you'll see is basically your spreadsheet after the macro. Okay, the space loads again are isolated, and I've only shown the cooling because we're going to do the package unit selection. So you will likely have the heating in here already, or you should if you did the homework correctly, but I want to avoid confusion, so I'm just going to show the cooling for now. And you have your room airflows calculated based on the set point temperatures of the room and the supply air temperature that you assumed at 55 degrees. So you should all have this information in your spreadsheet. And what we need to look at now is what is the block load of the spaces in your system. And remember, this does not equal the sum of the peaks in your spreadsheet. If you add all of these together, the space sensible loads, it will not equal the block load of the building, this value here. Now, this system checksums report is a different report from the spreadsheet that I showed you on the previous slide. So they're a little bit different. Don't think they're the same. The point of this slide is just to show you where you can get the block space sensible load for the building. Now, a couple of notes about the block and the peak loads. One, they are different. We've already talked about that. In the ventilation air portion of the block and the peak loads, the ventilation load is different. In the peak scenario, the conference rooms are all full. But in the block ventilation load, we do account for the fact that, just like in the block cooling load calculation, we account for the fact that some of the conference rooms are going to be filled by people who come in from other spaces within the offices. And again, just like in the cooling load scenario where we create two alternatives, we do the same with the ventilation scenario. Large conference rooms or training rooms should be considered full in the block load because typically in a training room scenario, for example, people like in a classroom in a university, the students who occupy the desks do not have offices within the building. So they are going to be coming from outside the building, filling the desk, filling the classroom desks rather. And that is not going to be an occupant decrease in any other area of the building because they're going to be coming from outside the building and sitting in the class. So what's true for the ventilation load, the point of this slide being what's true for the ventilation load is also true for the cooling load, which we learned before with respect to occupancy. So calculating the outdoor air, I am going to show you what we do in the spreadsheet. I'm adding some rows, as you can see here in the assumptions list. And I'm using the room area, adding a column to the spreadsheet where I have the ventilation CFM. Now, if you used, let me just make a quick side note. If you used this spreadsheet for your VA VBOC schedules, which is totally fine and wonderful, you might already have a ventilation CFM calculated. So that would be fine. You can use those numbers as long as you make the adjustments that I'm talking about to account for the block load. Because when we sized the VA VBOXes, we were using the peak load for ventilation. So again, if you've already done some of this, you can use it for your, if you've already done some of this for your VA VBOX schedules, like we learned in Duct Design Class 4, that's fine, but you do need to make some adjustments to make it a valid block ventilation load rather than the sum of the peaks. So I have added the area criteria here, 0.15 CFM per square foot, and I've added a column that then calculates the ventilation air based on 0.15 CFM per square foot. Now, what do I do about individual rooms that have more than 0.15 CFM per square foot during the block load? Well, I manually change them. Okay. Now, again, if you've already done this in your VA VBOX schedules, you might have done this already based on occupancy. I'm pointing out here the kitchenette. If the kitchenette has an exhaust fan, which is greater than 20 CFM, then I would actually put in the value of the airflow of that exhaust fan. Okay, that's the reason I pointed out the kitchenette on this slide. If you have a training room in your, or a classroom in your project, then you could manually change the ventilation CFM to a higher value in this column. Okay, so I didn't change any of these ventilation values in column E of this spreadsheet, but again, it would be the way to do it if you have a room that has a higher than 0.15 CFM per square foot ventilation load during the block peak. Okay, now the question is, for the ventilation load, we have to know what the outdoor air conditions are. The ventilation, as you remember from our definitions many lectures ago, is really another word for outdoor air. During the block load of the building, the condition of the outdoor air is given to you here. Okay? The month and hour, so this is for this building is July at 6 o'clock, is given at that point. 18 is based on a 24-hour clock. And here you have outdoor air, dry bulb, wet bulb, and humidity ratio. That's 77, 66, and that's given in grains, 80 grains. So the dry bulb temperature outside when your building hits block peak load is 77 degree dry bulb and 66 wet bulb. Those are the two numbers that are important for this exercise. So that's how to get the outdoor air conditions of your building when it peaks on the block load. Now, the question is, why is this outdoor air value different than the outdoor air criteria that you put in or entered in the weather criteria section of the load calculation program? That's the question. Now, if it's not different in your system checksums report, then you are extremely lucky, because almost all the time the outdoor air dry bulb and wet bulb given to you on the system checksums report here when your building peaks based on block loads is different than the weather criteria that you entered in the load calculation program. So I'll pause or if you want to pause the slideshow for a second and think about that, I'll give you the answer in 1 second. All right, I'm going to start again. The reason that this is different is because the block load of the building is a function of the outdoor air temperature, but it's also, excuse me, it's also a function of other things like people, computers, and so on. The building, especially if it's made out of concrete, and almost all buildings are in Northern California, will have what's called like a thermal mass, which causes a capacitance. So even though it's very warm outside, for example, it takes a few hours for the heat to impugn on the outdoor concrete of the building before it actually gets into the space. It takes time for that heat to travel through the concrete. And that time can be several hours. So when it's very, very hot outside, let's say at 2 p.m. or 1 p.m., the heat from that peak temperature of the day will not penetrate the concrete until several hours later. And that's why often we have a peak you can see here at 6 o'clock. It's late in the day, but that's because the building has a thermal mass. So when it was much hotter at, like, let's say 2 p.m. in this building, 1400 hours, the heat didn't immediately enter into the building. There was a capacitance effect due to the mass of the walls and the roof and so on. And so that's why it takes a while for that heat to get through. And that's also why typically your outdoor air dry bulb and wet bulb temperature will be lower than the weather criteria that you entered in the load calculation program weather pages. Now it could be higher. Okay, I'm not saying that it's always lower, but typically it's lower. All right, the next question is, does this value change on different systems serving the same building? So the question is, if you have 2 air conditioning units serving your building, will this outdoor air dry bulb and wet bulb temperature, will this time of day and month change if you have more than 1 air conditioning unit serving a building? You can pause the slideshow now and answer that question for yourselves. I'm going to go on. The answer is yes, it will. If you have an air conditioning unit that primarily serves the eastern side of a building, well, that air conditioning unit's block load is going to peak closer to the morning hours when the sun rises and penetrates through the windows and hits the exterior of the building on the east side. That's going to take a heavier load in the morning than, for example, the west side. So if you have 1 air conditioning unit serving the east side and 1 serving the west side of a building, the eastern side of the building is going to peak at an earlier hour than the west side, and for that reason the outdoor air dry bulb and wet bulb temperature of the outdoor air for the eastern building is going to be different than it is for the outdoor air condition of the western side of the building. Now in your projects, I don't want you to worry about that. Let's just make it simple and assume that we have one outdoor air condition for ease of calculation. But that's something to keep in mind when you design other kinds of systems for real building applications. So here's what we're going to do in order to calculate the entering air temperature going into the cooling coil of the air conditioning unit. We are going to assume a return air temperature, and it's okay to use the room set point as the return air temperature because the return duct is typically insulated, and so there's not a lot of heat gain as return air makes it back to the unit. Okay? If you want to be safe, you could probably add a degree or two to that. For the purpose of this lecture, we will use the room set point temperature as the return air temperature going back to the unit. So, what we do next is we calculate the wet and dry bulb temperatures of the mixture of return and outdoor air. Okay? In the psychrometrics lectures, I believe in the last lecture, we talked about the equations to calculate properties of air when you are mixing two air streams. So you can refer back to that. The wet and dry bulb temperatures of the return air, again, the dry bulb temperature is in this lecture is going to be the room set point. So I'm also talking about relative humidity there. You would take out a psychrometric chart. You could probably assume 50% relative humidity in the room at 72 degrees, which is what our return air condition is in this exercise. And then you could take that as your wet bulb temperature. So you're going to calculate the wet and dry bulb temperatures of the mixture of the return and the outdoor air. And again, the outdoor air condition is taken from the system checksums report. So once we've determined those values, we have what's called the entering dry bulb and the entering wet bulb temperatures. Now, just to help you understand what that means, this is a schematic of a package unit. This section here is called an air side economizer. We're going to learn about those a little bit more later. But essentially, the return air comes here into the unit. It goes through a mixing damper. The outdoor air comes here, and this is the mixing chamber. This is where they're going to be mixing. The return air and the outdoor air streams mix here. And it's at this point where you have the parameters known as the entering dry bulb temperatures and entering wet bulb temperatures of the unit. Now, the reason that those are important is because in the United States of America, in the catalogs for air conditioning equipment, that's what they refer to as the entering condition to the cooling coil. So if you call up a package unit manufacturer and you ask them to help you size an air conditioning unit, they're going to ask you, what are the entering conditions? They are not talking about the entering conditions here or here. Okay, they are talking about, when they say entering conditions, they're talking about the conditions of the air as it enters the coil of the unit. All right, it'll go through the cooling coil. We'll get some heat added by the supply fan. We're going to talk about that a little bit later in the lecture, and then it goes into the building and then back again. Okay, so that's what it means to say the entering air of a system. And now we can move on to calculate the ventilation load which was the third prerequisite that we need to size a package unit. We have all the information. We're going to use the sensible heat equation. Recall the sensible load, and this is in imperial units, so this is in BTUs per hour, is equal to 1.1 times the airflow in cubic feet per minute times the temperature difference in Fahrenheit. So the question is, what are T sub A and T sub B in the equation? What should they be in order to calculate the ventilation load? If we are looking at TA and TB, we have some options. We could say it's the outdoor air temperature at block load. We could say that the outdoor air temperature in the basis of design is one of those parameters. We could say the temperature TA and TB could be, one of them could be the return air temperature, could be the supply air temperature. Again, if you go back to that air conditioning unit schematic, let me just do that real quick. When I say supply air temperature, I'm talking about here. Okay, so we have some options. Could be the room temperature, could be the mixed air temperature. So we have six temperatures here that I've listed. My question is, and I'm going to allow you to pause the lecture if you'd like to think about it, what are the values of T sub A and T sub B in this equation to calculate the outdoor air load? Which of these 6 temperatures should we be plugging into those 2 values? That's the question. So think about that for a minute. I'm going to move on. And the answer is that it depends on what value you use for the airflow. The value that you use for the airflow is going to affect the values that you use for the temperatures. So if the outdoor airflow only, the ventilation airflow in other words, is your CFM, then T sub A is the outdoor air temperature at the block load and T sub B is your room temperature. That's how you get your ventilation load. Final question there for you to think about. What if you don't use the ventilation airflow? What if you use the total airflow of the unit? Would that change what T sub A and T sub B become? The answer is yes, it does. It does change it. If you use the total air conditioning unit's airflow in that CFM, then T sub A becomes is still the outdoor air temperature at block load, but T sub B becomes the mixed air temperature, not the room air temperature, not the return air temperature. Think about that. I'm going to move on to the fan heat. So here we have a circular problem. The fan heat is a function of the package unit that you select and the airflow. The package unit that you select is a function of the airflow and the fan heat. So do you see how we have a circular problem here? It's very similar to this equation here. E to the x equals the natural log of x. It is not mathematically possible to take that equation and solve for x. Okay? I believe that this is called a hyperbolic equation in math. Don't quote me on that, but I believe that's the class of equation that this is. When you cannot isolate x on one side of the equation, you have a problem. That's what we have here. Okay, we have a circular problem. To solve a problem like this, or to solve a problem of finding out what the fan heat is, we have to make an initial guess at what X is, and then we have to iterate. Okay? We have to make an initial guess as to what X is, and then we have to iterate. When we iterate, we will converge to a solution. A lot of fluid dynamics and heat transfer problems are like this. CFD programs, other kinds of fluid dynamics programs, heat transfer programs, all iterate and then try to converge, because this is a very typical kind of equation that you get in fluid dynamics and heat transfer and thermodynamics. So here's the protocol for how we will iterate. We're going to assume a supply air temperature that's delivered to the rooms, and based on that supply air temperature that we assume, we are going to calculate the airflow for each room. And then we are going to add all of the room's airflows together. So in your projects, you've already done this. And the initial temperature was 55 degrees. Now remember, we're talking about the block load. Okay? We are going to address that problem a little bit later in the lecture. If you sum all the airflows on your spreadsheet, you are summing the peak loads. But again, don't worry about that for now. We are going to address that later. We are going to assume that the fan adds 4 inches of pressure to the air. Okay? Now, this is not the external static pressure. Okay? This is actually the amount of fan heat that's added is based on the total pressure, internal and external, that the air conditioning unit's fan has to overcome. We are going to lock that value in at 4 inches. In a real job, for example, you would need to calculate this. You would need to do a pressure drop calculation of your duct system. You would need to look at the package unit catalog, which would give you the internal pressure drops across filters and coils and such. And then you would be able to calculate the pressure across the fan. We're going to assume that the fan efficiency is 65%. We're going to lock that in. Again, this is something that we can determine through looking at the manufacturer's catalogs, but for this exercise, we will lock it in. We will not change it. And this is the then equation for the fan heat. We calculate the brake horsepower, and using the horsepower of the fan, the brake horsepower, and this value, 2545 BTUs per hour per brake horsepower, we get the fan heat in BTUs per hour. Now, what do I mean by brake horsepower? What does that mean instead of horsepower? The brake horsepower is, the best way to think of it is using the name. It's very intuitive. It's the amount of power that's required to stop the fan when it's running at a particular speed. Just because a fan has a 10 horsepower motor, it does not mean that it's using full power. It could be using 8 horsepower. Typically it's using less. So we learned in the fan selection lecture, where we were learning about types of fans, we learned that the brake horsepower is different than the overall horsepower of the fan. So the fan heat is a function of the brake horsepower. It's not the overall horsepower of the fan. Make a note of that. Now, we're still moving on here, selecting this package unit, which is laborious, but after you do this a few times, it'll go very quick. So, from the previous slides, we have the space loads at the time of the block load. That's from the system checksums report. We have the outdoor air load, and we have the fan heat. We are not exactly done yet. Now we still have to start the iteration process. okay? If we add those three quantities together, we get the actual load that the package unit has to overcome. Okay? So adding those three components together, we get the actual load that the AC unit must overcome. And on the following slide here, you can see that I have calculated this here. So I've added a column H. I've called it calculations. Before I had a column here called assumptions. I've listed all my assumptions here. Most of them you will recognize from the slides that we talked about. And in column H, I've added another section called calculations. And you'll recognize most of these calculations, well, not most of them, all of them, from the previous slides that we just talked about. So you can build this and you'll get to this value here, which I've listed at 77,430 for this example. That is the cooling load that the air conditioning unit must overcome. I'll give you a moment to think about that. If you'd like to pause the lecture to look over them or go back through the slides, that's your choice. I'm going to move on. Now we have to find a package unit that matches this load. Manufacturers publish the sensible heat capacity of the units based on airflow, condensing temperature, meaning the outdoor air temperature, and the entering, dry, and wet bulb temperatures of the units. Okay? A very important note here. The whole purpose of this lecture is basically summed up in this note. Okay? Package units are not custom built. These are commercially available products that are the same when they come off the assembly line. If you buy a 50-ton unit, it doesn't matter where you buy it from. If you buy a 50-ton, let's say, Trane or Carrier or York unit, it doesn't matter where you buy it from, it's the same thing. It does not exactly match your system checksums report. You can't just say, here's my system checksums report. It tells me that I need a 50-ton unit, for example, so then I'll just select a 50-ton unit. That's not the way this works. You have to engineer the unit for your load because they are not custom built. So you have to configure it and figure out how it can match your load. This is why we have to iterate. And in this protocol, we are going to iterate based on the AC unit's total airflow by changing the supply air temperature. Now that might have gone over your head. It probably did. Don't worry, we're going to go through the protocol step by step in the following slides. Okay, so using the parameters, we're going to find a unit that will handle the sensible heat capacity that we require. We're going to use the condensing temperature, entering dry bulb and entering wet bulb temperatures. When we find a unit that can handle the sensible heat capacity, we will read in the manufacturer's catalog what airflow that unit requires to satisfy this capacity. We're going to let the unit manufacturer tell us that in order to satisfy that load, this is the airflow that the unit must run at. Okay? Using that data, we are going to recalculate the supply air temperature. After the manufacturer has told us what airflow to use, we're going to go back into our spreadsheet and recalculate the supply air temperature so that our system has the same airflow that the manufacturer specified. Okay, now we iterate. After we've entered in the new supply air temperature into our spreadsheet, it will have recalculated, because we've linked it in the spreadsheet, all the calculations are linked. It will recalculate the fan heat, the ventilation load, mixed air temperatures, so forth and so on, and it will give us a new sensible heat capacity. We will then go back to the manufacturer's catalog, get a new airflow using that sensible heat capacity, recalculating, and so forth. And that's how we're going to iterate. There's some sample files that you can open up to look at. I'm going to be referring to them through this lecture. I'm going to be switching back and forth. They are not embedded in these slides, so you will need these documents, and they should be available to you if you're watching this video. If not, contact me. One is the sample checksums SB30 document, and the other one is the sample AC unit iteration SB30 document. Okay, from those reports, which I included in previous slides in this lecture, you can see that the condensing temperature the outdoor air temperature at peak is 77 degrees. Let me switch over to that document right now. Just center it here for you. So up here is where my cursor is. You can see that it's 77 degrees. I am going to add 8 degrees to that value to account for a dark roof. So my condensing temperature that I'm going to use in the catalog is going to be 85 degrees Fahrenheit. And again, from that system checksums report, you'll see that the space load is 592,000 BTUs per hour, or close to that anyway, and that's from right here where I've clouded in red. And then from the calculations in the spreadsheet, using an entering dry bulb temperature of 75 and an entering wet bulb temperature of 60, I get an AC unit airflow of 28,730. Okay, I'm not going to go through these calculations. I just described them earlier, but I had I think it was a 72 degree air room set point temperature. So using these values, these are the entering conditions that I get. So my AC unit airflow becomes 28,370 CFM. And the minimum AC unit sensible capacity based on that airflow is 687,131. The system checksums report shown here, shows you here is the space sensible loads. That's the number that you'll see in the slides that we just talked about. As far as the calculations go, those are depicted in this spreadsheet. You see here the assumptions column. The space load, I've listed it in the assumptions column. It is a calculated value, but it's not calculated in the spreadsheet. It's a number that comes from somewhere else. And so that's why I've put it here. When I list calculations in this row, or this column rather, I'm referring to calculations that are done in Excel. So you can see I've calculated the airflow based on the spaces below that are not shown, calculated the outdoor air load. Again, every time I change something here, it will automatically update all of these numbers. So I've made all of these calculations. There's the airflow calculation that we talked about. 28,367 fan heat, and then the overall capacity of the unit, the sensible capacity of the unit, is 687,000 BTUs per hour, which is 687,000, yes, 131 BTUs per hour, which is what we spoke about on the previous slide. So now what I'd like you to do is to open the Trane Rooftop Package Unit Catalog document. If you don't have this, I can send it to you as I can all these other PDFs that I've been referring to. If you go to page 73, you'll see the cooling capacities of a 20-ton standard capacity unit. Now that rooftop unit catalog looks like this. That's the front page, or the page 1. It's from April 2017. I'm not sure when you're viewing this video. This might be outdated, but it doesn't matter. The principles are the same universally among other manufacturers. You know, we're using Trane here. Carrier and York and McQuay and Petra, Lennox, all of them are the same in terms of the data that they give you and the method by which you would size the unit. And again, if this data is out, is not updated, it's okay, because we're just kind of going through the methods, not necessarily trying to make sure that it's all up to date. So if you take that catalog, and again you go to page 73, you'll find the cooling capacities for a 20-ton standard capacity unit. I have a snapshot of it on the following slide. Now, I'm describing here how I would evaluate the unit. So in the previous slide, we determined that we needed 687,000 BTUs per hour of sensible capacity. And you'll notice on the following slide that the maximum capacity that the 20-ton unit can deliver in our conditions is 222,000 BTUs per hour, which is much, much lower than what we need. So let's jump over there. This is all from the calculations on the spreadsheet. So we have 85-degree ambient temperature, which I've described earlier. We have a 61-degree outdoor wet bulb temperature. I'm sorry, this is the entering wet bulb temperature. It's not the outdoor temperature. The outdoor temperature, I believe, was 60 degrees, or else the calculated value was 60 degrees in the spreadsheet. Let me just go back there just to make sure that I'm not. So our mixed air conditions entering are 75 and 60. Okay, so you can see in the catalog that I am using the entering dry bulb temperature of 75 and the entering wet bulb temperature of 61, in spite of the fact that the calculation showed it was 60. So I'm just basically saying it's close enough, right? 1 degree off, you would not try to interpolate or extrapolate this table out to see what the increase in capacity would be. With a lower entering wet bulb temperature, you will get higher capacity. You can see here for the same entering dry bulb, the sensible heat capacity is substantially reduced when the entering wet bulb temperature is 67. So 61, it becomes 145 at this 4,000 CFM airflow. If it was 60, it would be slightly higher. Again, I'm not going to extrapolate because 60 is close enough to 61. So with this 20-ton unit, standard capacity, we have here 20-ton unit standard capacity. We have options. We can run the unit at 4,000 CFM, 6, 7, 8, and 9,000 CFM, which are given to us. In the table, obviously, we can run between these airflows. That would just mean that we would have to interpolate between the numbers to get our exact capacities, So you can see that the 20-ton unit, even at maximum power, 9,000 CFM, maximum cooling, only is going to give us 222,000 BTUs per hour, which is about 1/3 of what we need, which obviously means that this 20-ton unit is too small. So on the previous slide, I mentioned that once you find out that the 20-ton unit is too small, you would then move on to pages 93 and 94, where we are looking at 60 and 70-ton units. And I have those snapshots in the snapshot following the 20-ton unit. So this is the 60-ton unit option. And then the next slide shows the 70-ton unit option. So let's just look at the 60-ton unit option. 85 degree on the roof. This was something mentioned in a previous slide of how we got that number. 61 entering wet bulb and 75 entering dry bulb. And again, you see we have options as to how much air we flow through the unit. Now we want 687,000 BTUs per hour. You can see that at full power, the 60-ton unit gives us 679,000 BTUs per hour, so we're slightly lower. And for that reason, we are going to start with the 70-ton unit. And then we're going to go back to the 60-ton unit. And the following slides describe this process. So we're short by about 1% when we choose the 60-ton unit. So we go to the 70-ton unit page, and we see that it can easily deliver 687,000 BTUs per hour. And after interpolation, we find out that the airflow at which the 70-ton unit gives us 687,000 BTUs per hour of cooling, given our entering and ambient conditions, is 22,265 CFM. So here's where the iterating begins. We solve for the supply air temperature, we solve for the supply air temperature using this 22,265 CFM and our space load. Remember, the airflow temperatures are the leaving temperature out of the unit is a function of the space loads. Okay? I want to make sure that you understand that. That's why we have 593 in here and not 687. 687 takes into account fan heat, outdoor air load, and so forth and so on, something that the space won't see. So that's why we use the space load and this airflow to determine what the supply air temperature coming out of the unit is going to be. And we find that the supply air temperature coming out of the unit is 49.8 degrees. So our initial assumption of 55 degrees is much higher than 49.8. So we plug 49.8 into the spreadsheet and recalculate the numbers. So what that would mean is you would come back to this spreadsheet and you would enter in this cell, assumption A, you would enter in 49.8 degrees. What that would do is it would update all of these numbers. And once it updates all the numbers in the spreadsheet, you'll get new conditions, new fan heat and so forth. And what you'll realize is that the sensible capacity of the unit is now required to be 672. Remember, before we were at 687, now we're at 672. The reason for the reduction is because we have less airflow, and meaning we have less fan heat. Okay? So this gives us the same entering conditions, conspicuously enough, 75 degree dry bulb, 60 degree wet bulb. So we go back in to the catalog, but this time we realize that we can use a smaller unit. And so let's go to the 60-ton unit. We repeat the process again, and we realize that the 60-ton unit can satisfy our load at 26,635 CFM. We resolve for the supply air temperature like we did before, and we get 53.76. Now, an item of note, if we would have stayed with a 70-ton unit and not dropped down to a 60-ton unit, we would have converged. You would go back through the process again one more time, but you would see that it would result in the same supply air temperature. You would have converged. Because we switched the unit size, now we're back in the process of iterating. We're kind of jumping around instead of maintaining the supply air temperature very close to what we had before, which is what would happen if we converged. Excuse me, I'm not sure why that's happening. Instead of having a supply air temperature that was very close to what we calculated before, indicating convergence, we are now much different because, again, we switched the unit size. So we go back to the spreadsheet, plug in 53.76, and we get new numbers. Our new conditions will become that the AC unit sensible capacity required is 682,838, and our entering conditions remain the same. Using the 682,000 BTU per hour load, we realize that the unit can satisfy the load at 27,000 CFM. And once we recalculate the supply air temperature, we're at 54.0 degrees. Recall from the previous slide, we were at 53.76. Now we've jumped up to 54 degrees, but basically that is a 1/4 of a degree Fahrenheit change. That means we have convergence. Okay? And as I mentioned before, if we would have stayed with the 70-ton unit, then instead of 49.80 degrees, if we would have plugged in our new airflow and run through the calculations again, we would have ended up with a supply air temperature of 49.79 degrees, in other words, a 0.01 degree Fahrenheit change, which again would indicate that we have convergence. So you can use either unit, the 70-ton unit at 22,400 CFM. You'll get a different supply air temperature, a lower supply air temperature. Or you could use the 60-ton unit at 27,000 CFM, and you'd have a higher supply air temperature. Either one will satisfy the load. However, depending on the unit you pick, they will operate at much different supply air temperature conditions. And again, this is the part of engineering where you match the equipment to the application. It's not enough to just run a load and then pick a unit and then run with it. You need to know what your supply air temperature design is. The controls contractor needs to know that. For example, if you pick the 70-ton unit and you have a need at peak block load to run the unit at 49.8 degree Fahrenheit supply air temperature, and you don't tell that or communicate that to the controls contractor, well, the controls contractor is going to use a standard rule of thumb and just set the unit lowest supply air temperature to 55 degrees. Well, guess what? At 55 degrees, there's going to be problems on a hot summer day. So you need to communicate this kind of thing, how the equipment is supposed to operate given your application. If you don't do that, then people will use rules of thumb in order to complete their tasks, and then the building won't work, and it will be the engineer's fault, the mechanical engineer's fault, not the controls engineer. So a couple of considerations, some of which I've mentioned. If you change tonnage in the middle of an iteration process, it will take longer to converge because the different sized units will bounce the supply air temperature, if you will, to a different value. So the lesson is to change the supply air temperature, is to change the unit size during an iteration only when necessary. Second consideration, the airflow requirement of the larger unit is 20% less than the smaller unit to achieve the same cooling capacity. So, excuse me, if your job necessitates minimizing duct sizes, then you would choose a larger unit. And note how we have ignored the latent capacity. This is correct in Northern California because we don't have to, design for outdoor air humidity extremes. So we really only focus on the sensible load. In other climates, that would not be the case. So you do have to consider the climate that you're in. But in Northern California, and probably all of California, I could safely say, we do not take into account the latent capacity of the unit. Now, as I've mentioned before, several manufacturers have selection programs. So you can plug in some conditions and the program will select a unit for you. The program will essentially go through the steps that we just went through, given certain input data. What I am suggesting and advocating is that it's very important to do these selections by hand, because you will learn how the different parameters of an air conditioning unit affect its capacity. And I've given a couple examples here. Okay, the airflow you saw in the example that we just did, the airflow needs to be a variable. What we're concerned about is cooling the building, meeting the load, keeping people comfortable at a certain temperature. If you use a computer selection program and you input the airflow, you are going to artificially limit the air conditioning units that could satisfy the application. But you wouldn't know that unless you select this air conditioning unit by hand. You wouldn't understand that varying the airflow between different sizes of units can satisfy the load, and it gives you more flexibility and more avenues to be creative as an engineer designing an HVAC system for a specific building. So here, without understanding that increasing airflow can significantly change capacity, a user of the program would not try a smaller sized unit at a higher airflow just to see if it could work. Okay, you're basically a slave to the selection program. Whatever output options it gives you, you're going to select one of those units. And when you do it by hand, you can see the tables in front of you and you can know how close you are, for example, to selecting a smaller sized unit that might be able to work. Thank you for listening and have a wonderful day.